All right, here we go. The last section, chapter 12, section 2 is on analysis of variance. So ANOVA stands for analysis of variance. Previously, we were able to test claims about two means, like mean 1 equals mean 2. Now the idea is, what if you have more than two means? What if you've got three or more means that are claimed to be equal? So a claim would look something like this: mean 1 equals mean 2 equals mean 3. We're not going to write down the alternate hypothesis or H sub O, we're just going to use the claim. Okay, so to do this, you're going to have to either be given the mean and standard deviation or find it yourself, which I'll show in just a second with the example. And we are going to be using variation or variance to see how much do the three means vary, and also how much variation is there within the individual scores. So for example, if you have three basketball players and they average 30 points per game, well, if there's one player that's very inconsistent, scores 50 points one time, 12 points another time, you have to take that into account. How much variation is there? And then we're going to make the test statistic, which is capital F, and the critical values are in table A5. You'll find table A5 in the back of the book. It's not on the formula card, it's in the back of the book. So that's where you look for it. Okay, now on to the example. So the questions pretty much have to say something like this. It's got to say the word ANOVA in there, and then ANOVA means it's going to be a claim of equal means. So here's an example, and I just made up these numbers. This could be ages of people or something like that. I guess it could be basketball scores for individual people, but anyway, let's just say it's ages. So as you can see just by looking at the numbers, these people are younger and these people are older. So it should be that the means are not equal. So at the end, we should get reject the means are not equal. Let's see. The first thing to do is type these into a list. I use list 1, list 2, and list 3. And then find the mean and standard deviation on the calculator. So here they are. And as you can see, the average here, 19.8, definitely different than 29.2. But you have to, for one, consider how much variation is there with these three numbers. And we also have to take the standard deviation into account. Okay, and don't forget that variance is standard deviation squared, and it's just a way to measure variation. In English, plain English, we usually say the word variation. In statistics, we use the word variance. All right, so I just copied and pasted. There's the means and standard deviations. And the first thing to do is find out what's the average of the three averages. That's called the overall average. So just add them up and divide by 3. We can do that quickly, 23.867. And then we're going to see for these three means up here, how much do they vary away from 23.867. So variance means we're going to have to square them. So you subtract each score from the mean, square it, add those three up, divide by n minus 1. And we get a 23.29. All right, we'll come back to that 23.29 in a second. Now what you do is take the standard deviations, or when you square it, it's the variance. Take the variances into account. So take each standard deviation and square it, add those up, and divide by 3. We get a 4.897, which also we'll use in a moment. So here's the test statistic, capital F, and it's the variance of the means, that was the first one we found, divided by the mean of the variances, the second one we found, and then you multiply by n, which is the sample size. In here, that's 5. So this symbol right here, since it's s squared, that means variance. And then it has x bar because it comes from right here using the x bar or the averages. And on the bottom it is s squared, so that's also variance. And then p means pooled. So if you put the variances together, which we did right here, and averaged them, the bottom part would be 4.897. Okay, so just a recap of that, and then we're ready. The test statistic. So you put the numbers into this little formula, get out a calculator and divide it, and the test statistic is 23.78. Next, we need to use table A5, which we haven't done before. This is a right-tailed test only, so whatever alpha is, that goes for the right tail. The formula for, there's 2 degrees of freedom. The formulas for degrees of freedom are pretty short, sweet. There is the number of categories, and we had 3 groups, so this would be 3 minus 1. And then the number of categories, 3, times the sample size of 5 minus 1. So in this case, it would be degrees of freedom 1 is a 2, degrees of freedom 2 is a 12. Next, take a look at table A5, which looks like this. It's 0.05 in the right tail only. There's a little reminder right here, right tail. And then degrees of freedom number 1 goes across the top. So you look for the 2, that's here. And then on the side, you look for 12. And so that's right here at 3.8853. Now we're ready for the picture. So the F distribution looks like the chi-squared distribution. It's a right tail only, and there's degrees of freedom 2 and 12. Critical value, which we just looked up, 3.8853. And then a minute ago we did the test statistic, which is 23.78. That definitely goes way past 3.88, so we reject. We did actually prove something. And we proved that the 3 means are not equal. Okay, the last thing to do is use the calculator. Rather than using all of those formula, you can use the calculator. Again, you'll need to put the numbers in the lists. I would prefer to use list 1, list 2, list 3. And then use the Anova test. So here are the numbers in the list. List 1, list 2, list 3. There's the original data. And then you go to Stat, over to Test, move down to the bottom of the list and find Anova. And then you just need to tell the calculator list 1, comma list 2, comma list 3. And then it will do the calculations for you. Notice that this F is just slightly different than what I got. The calculator right here that you see on the screen is more accurate than when I used the formula. When I used the formula, there's a little bit of rounding error. Not much, but a little bit. This is more accurate. It's easier and it's more accurate. That's what more could you ask for? And you could see degrees of freedom is 2, and if you scroll down, you'll see degrees of freedom of 2 and 12, and that's everything you need. All right, so that's the Anova. See you soon.